So welcome back. Let's continue with chapter 12. Last time we discussed the different intermolecular forces. We talked about dispersion, dipole-dipole, hydrogen bonding, and ionic, going from the weakest to the strongest on that regard. So before we leave those definitions behind, let's do a problem from the book. And this problem, I used it once in one of our tests. So the question is, which intermolecular force is represented in the following figure? And explain. Well, how do we answer this? Well, what are the intermolecular forces? They're going to be dispersion, and we know that any matter will exhibit dispersion because it's due to the movement of electrons, and all matter contains electrons. And then we have dipole, which is when you have a polar molecule that is influenced by another polar molecule. Then you have hydrogen bonding, which is a super dipole, and that only happens when you have fluorine with hydrogen, oxygen with hydrogen, or nitrogen with hydrogen when you're having fun. And the other one is the ionic one. So based on what we know about these forces, what is required, for example, the dipole requires a polar molecule, a dipole. Let's look at this. So we have this being attracted by intermolecular forces to this, being attracted by intermolecular forces to that. And what do we see here? Well, it seems to be showing a nucleus and a pair of electrons. There's only one nucleus, right? So to be a molecule and therefore be able to be polar, it had to be at least two nucleus connected in a compound. So this is an atom. So an atom is not a molecule, therefore it cannot be a dipole. If it cannot be a dipole, it cannot be hydrogen bonding, given that hydrogen bonding is a special type of dipole, and therefore it's not ionic. So what we are seeing here is dispersion. So on this particular atom, because you have a nucleus and electrons, the electrons happen to be at one particular time only on one side, which makes this partially negative, while the one that is lacking becomes partially positive. And the same situation repeats with that, and so on. So this is definitely dispersion. So this was probably a 10 to 20 point questions, because if you said dispersion, excellent, you got 1 point out of 20. On the explain is where you're gonna get your other 19 points. So if you talk about all the different forces, what each one requires, and then you realize that this is just 3 atoms, and therefore it has to be dispersion. If you show everything you know, you got your 20 points. So far we have been able to identify the intermolecular attractive interactions. We have been comparing the relative strength. We haven't talked about polarizability. So let's say, for example, that you have a molecule of oxygen. That's basically a oxygen connected to another oxygen. Electronegativity is 3.5 on both sides. 3.5 minus 3.5 equals 0. So this is a non-polar bond. So this molecule is non-polar, is even, everything is evenly distributed. So it's a non-polar molecule. So the only thing that these molecules have going for it is dispersion. However, let's imagine that, for example, we bring this close to KCl, where it's composed of a positive and a negative. This positive is going to attract the electrons. So what this positive is doing is polarizing the cloud. By polarizing the cloud, the oxygen molecule, which is even non-polar at that particular moment where the K plus is attracting those electrons, at that particular moment, it becomes partially negative and partially positive. The cloud have been polarized, and now it can exhibit dispersion forces. So that's what we call an induced dipole. The potassium by itself is distorting the electronic cloud, creating a dipole, which shouldn't be because it's a non-polar molecule. So that's what we call polarizability of the electron cloud. So leaving that behind, we move into the next objective. Explain the concept of boiling point, vapor pressure, viscosity, surface tension, and capillary action. And we're going to explain this by using what we just learned about intermolecular forces. First thing, let's make sure we clarify this. This is a very common misconception, so we have to clear this right away before we proceed. Imagine you have a beaker full of water. So this beaker is full of water. And you have it on a stove at the highest setting. So you put in a lot of heat into it. So what happens there? Well, this is partially positive, like we already know, and this is partially negative. So you have an intermolecular force in there. Partially positive, partially negative. Another intermolecular force. Another one here. Another one there. So all those molecules are attracting each other. So they form like a network by the pure magnetic attraction. So if we are boiling this, what's going to happen, since we are increasing the temperature, the molecules are moving faster now. So if I used to have a molecule, two molecules that were set up like this, and this was where the intermolecular force happens, if I warm it up, these molecules are going to start moving randomly faster and faster. So because they're moving, you probably end up with something like this. If you notice now, the alignment is not as good as before. Now you're going to have something more distant. So the more the molecules move, the worse the alignment is going to be to have that partially positive close to the partially negative, and the molecules are going to begin to separate. When the molecules begin to separate, now there's nothing holding them, and they're moving randomly, and if they happen to move toward the top, they're going to escape. And that's what we call boiling. The misconception I wanted to clarify is that some people, because it was never clarified for them before, some people think that this is boiling. You have a water molecule, you warm it up with heat, and then you get this. That's not boiling. That's a chemical reaction that destroys the molecule. Boiling is a physical process. Therefore, the constitution never changes. You get liquid H2O becoming gaseous H2O. But you do not break the bonds. So a lot of people, usually about 40% of my students, believe that that's what boiling is. So now that we know what boiling is, how does this relate to intermolecular forces? Well, the stronger the intermolecular forces present, the stronger that intermolecular force is going to be between molecules, the more heat you're going to have to apply to be able to disrupt that attraction, which means the stronger the intermolecular forces present, the higher the energy required to boil it, or the boiling point is going to be. What about vapor pressure? We know that water boils at 100 degrees Celsius. That's the boiling point of water. But let's say that on my floor, I have some water in there, and the temperature is inside my house, let's say around 27 degrees Celsius. So therefore, that water will never boil at that temperature. But how many of you have ever seen a little bit of water on the floor, and when you come back later, it's gone? The reason is that molecules are always moving, and every so often, one of them is going to escape. If we have reached the boiling point, all of them will have the energy necessary to escape. But since this is not the boiling point, only a very few of them will do that. But you let it go for a long time, eventually all of them are going to be gone, and it's going to evaporate. So if I had that same water inside a beaker, and this is a better way of seeing it, and I have my water there, and let's say that I put a wash glass on top, so kind of closing the beaker. So at any temperature, some molecules of water are going to escape. And when they escape, they eventually will hit that surface and they will bounce back. And some of them will bounce back to the surface. And since they're moving, when they hit the surface, they're going to hit it with a force. And that force is what we call pressure. Remember what we covered on Chem 1? Pressure is nothing more than the particles of the gas hitting the walls of the container. So in this case, the water vapor that escapes start building pressure against the surface. That's what we call vapor pressure. Does it make sense that that pressure is going to be higher at 98 degrees Celsius compared to 30 degrees Celsius? Why? At 98 degrees Celsius, you're putting more energy into those molecules, so they're going to move faster, right? So because they're moving faster, they're going to hit the surface harder, which is a higher pressure. So the higher the temperature, more molecules can escape, and more molecules will be hitting the surface also, so higher pressure. So that's what vapor pressure is. If this was an open beaker, then you will have air on the outside, and that air that goes all the way to the edge of our planet is what we call 1 atmosphere of pressure. So for this molecule to escape now, they're going to have at least the force of 1 atmosphere of pressure to be able to escape. So on an open container, the vapor pressure is going to be very different from on a closed container. So what the main point I'm trying to make is that vapor pressure is nothing more than the molecules of the liquid that become gas that are then hitting the surface again and putting pressure. And the higher the temperature, more molecules are going to escape, and the higher the vapor pressure is going to be. So vapor pressure is very different from boiling point. Boiling point is the temperature at which all molecules have enough kinetic energy to be able to escape or become gas. What about viscosity? Viscosity is nothing more than if you have a beaker with a liquid, how that liquid flows out. And you know that ketchup, for example, takes a long time to come out of the bottle because it's very viscous. Oil is very viscous. Uh, Water is not that viscous. So water compared to a pancake syrup, for example, is less viscous. And that's because the intermolecular forces are holding the molecules together, and they cannot, it's harder for them to go flow past one another. When they try to flow one past one another, if you have the proper combination and this molecule is trying to slide back by, the moment it starts going by, this intermolecular force is going to catch and it's going to prevent the fluid movement. So the stronger the intermolecular forces, the higher the viscosity is going to be. One thing I forgot to mention last time is that dispersion, the bigger the molecule, the stronger the dispersion is going to be. And the reason is that if I have two molecules that are big compared to two small molecules, you have the possibility of having intermolecular force all around the surface versus this here. So this will be a stronger force. So dispersion force increases with the mass of the sample. And if you remember, I told you at the beginning that dispersion force, which is the weakest one, sometimes it could be stronger than dipole-dipole because of the size. So if the size is big enough, the dispersion force resulting from all those connections can be a lot stronger than something that receives dipole-dipole. And then we have surface tension. Surface tension is nothing more than if I have a beaker with a liquid, for example, on the surface, there's molecules that are being attracted by intermolecular forces. And if I try to penetrate that surface, the stronger the intermolecular forces are, the harder it's going to be for me to go through. So, which means it's a high surface tension. The weaker they are, the easier will be to be able to go through. So surface tension refers only to the layer of molecules on the surface and how strong they can hold together to avoid something going through. And the classic example is the mosquito standing on water. If the water has enough surface tension, the weight of the mosquito is not going to be enough to break it and let the mosquito sink. But if I try to do the same, a whole different story. And capillary action. What is capillary action? Capillary action is the tendency of a liquid to go up a glass surface, for example. So if I have a test tube and I put water in there, that's not what you're going to see. What you're going to see is something like this, which we call the meniscus, right? And why is that happening? Well, that's happening because the glass is made out of molecules, silicates, that are very polar molecules. So water, let's say that this is water, right? So if we have water, Water is going to start being attracted by the surface, and that's going to cause the water to start kind of inking toward the top. And when one water goes, because of the hydrogen bonding, another one will follow. And as the higher this one goes, the more of them are going to start climbing the wall. So that's what we call capillary action. And it happens because the attraction between the liquid and the surface is stronger than the attraction between the liquid and the layers below. And that's what start going up, away from the rest. And all those are dictated by capillary action. So the stronger the intermolecular force between the glass and the liquid, the more it will go up the liquid, the higher the capillary action. So that's kind of a quick definition of all these properties that are influenced by the intermolecular forces. So let's do a problem. So arrange these compounds in order of its increasing boiling point. So the energy required for all the molecules to be able to escape from the liquid phase to the gas phase. The best way I like to do this is like this. I like to do a table in which I'm going to put the forces: dispersion, dipole, dipole, hydrogen bonding, and ionic. The more forces the molecule have, the stronger the intermolecular forces. And remember, we're not talking, for example, methane. These are intermolecular forces. It's what happens when you put two methanes together. Would you get intermolecular force between them? Well, let's see. Methane CH4, Lewis structure is going to be something like this. Carbon electronegativity is 2.5, hydrogen is 2.1, 2.5 minus 2.1 is 0.4, and from 0 to 0.4, we have a non-polar covalent bond, which means there's no pull for the electrons. This molecule is symmetric. So this molecule is nonpolar, which means it's a nonpolar molecule, so it cannot be a dipole. So two of them cannot be dipole-dipole. Therefore, it cannot do hydrogen bonding, and it's not going to be ionic because we've seen a difference of 0.4 for the bond. So it's going to have only dispersion. The other one is the same thing. It's carbons and hydrogen, so it's going to have dispersion. It's not going to be a dipole because it's not nonpolar, therefore not hydrogen bonding, therefore not ionic. The next one is a little bit different. The next one, the Lewis structure is going to be carbon, hydrogen, 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 carbon, hydrogen, hydrogen, and chlorine. So we know that this bond is nonpolar. We already saw it here. Nonpolar, 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 nonpolar. This is between two of the same, so nonpolar. However, this is 2.5, this is 3.0. So the difference is 0.5. Bigger than 0.4 is going to be a polar covalent bond, which means there's going to be some polarity there, which is going to make this partially negative and this partially positive. So this molecule contains electrons, so therefore dispersion, and is going to be a dipole. So this one is a dipole. Can it also have hydrogen bonding? HF, HO, HN, right? So that one doesn't have that feature, so no hydrogen bonding, no ionic. What about the next one? Well, the next one is a similar story. The next one is going to be CH3, CH2, OH. 2.1, 3.5. So this is definitely a polar covalent bond, which is going to make this partially negative, partially positive. So that's a dipole. So we're getting a dipole. So definitely dispersion. All of them have dispersion. It's a dipole. We proved that. And in addition, it contains one of those features there. So it also have hydrogen bonding. So based on this table, this one have 3 forces, this one have 2 forces, and these two have only 1 force. So I will say, let's say that this is 1, 2, 3, 4. I will say that 4 will have a higher boiling point than 3, because 4 exhibit dispersion, dipole-dipole, and hydrogen bonding, while 3 only exhibits dispersion and dipole-dipole. And then we have to choose between 1 and 2. Both of them only have dispersion, but this is smaller than this one. So this one have a bigger mass, just like what the sample I showed you for dispersion. So the dispersion on number 2 is going to be a stronger dispersion, therefore a higher boiling point. So that's how I recommend that you do this type of problem when you have to decide about one of these properties, like boiling point, surface tension, and so on. Determine the intermolecular forces present, and then evaluate the quantity, and then evaluate the mass to see if dispersion can be affected. So with that said, now you can do this problem. So continue the paper that you did from part A, daily work 12.2. You have 3 different problems. Decide on each one which one will have the highest boiling point. So let's continue. What about this one here? For each pair of compounds, pick the one with the higher vapor pressure. Remember, vapor pressure is the gas, the molecules that become gas. The higher the temperature, the higher the vapor pressure is going to be. But in terms of intermolecular forces, the stronger the intermolecular forces, it's going to require a higher temperature to vaporize them. The stronger the intermolecular forces, a lower amount of molecules are going to be able to escape. So the stronger the intermolecular forces, the lower the vapor pressure. And if this was a test, I will tell you that. So do not memorize that. Make sure you understand it and you can explain it. So between this and this, CH4 versus CH3Cl. So intermolecular forces, dispersion, dipole, hydrogen bonding, and ionic. We know that this one have dispersion. We already checked it on the previous problem. And we know that it's nonpolar, so nothing else for this one. This one here, Lewis structure is going to be something like this. based on the electronegativity, we know that it's going to be a polar covalent bond. So that's going to be a dipole. So if I have two of them, it will be a dipole-dipole interaction. So which one have the strongest forces? This one will have the stronger intermolecular forces. So it's going to be harder for the molecules to escape. So this one will have the lower vapor pressure. This one will have the higher vapor pressure because the forces are weaker, so more molecules can escape and join the gaseous form, which is going to put pressure on the surface after that. What about the next one? So for the next one, let's see what we have. For the next one, we have CH3, CH2, CH2OH, and CH3OH. So both of them will have dispersion. However, notice both of them will have hydrogen bonding, right? OH, OH. So both of them are going to be dipoles. Both of them will have hydrogen bonding. So what's the difference between them? This one is smaller, right? And this one is bigger. So this one will have more dispersion. So this one will be the one with the stronger forces then, which means the vapor pressure is going to be lower compared to that one. So both of them contain OH, which makes it polar. Therefore, hydrogen bonding because it's OH. But one of them is bigger than the other, so the dispersion force is stronger on that one. And what about the last one? So for the last one, let me clear the screen here quick. For the last one, we're going to have CH3OH. So definitely dispersion. That's going to be a dipole. And it's OH, so hydrogen bonding and not ionic. The other one is H2CO. So the first thing you have to do is make sure you know how to draw the Lewis structure. So carbon, 1, 2, 3, 4, hydrogen, hydrogen. And then I'm going to take this dot. I'm going to put it there. And I'm going to have my oxygen do something like this. 1, 2, 3, 4, 5, and 6. So this molecule, when I look at the central atom, is going to have bonded 3 and lone pairs on the central atom 0, which means it's going to be trigonal planar. So let me draw it again, trigonal planar. So it's going to be something like this. Double bond, hydrogen, and hydrogen. That would be my trigonal planar molecule. Based on the electronegativity, I'm going to have a polar covalent bond there. So this molecule definitely has dispersion, definitely have dipole-dipole. Do I see HF anywhere? No. What about OH? No. What about NH? FON, right? No. So no hydrogen bonding for this one, no ionic. So therefore, this one contains 3 forces, this one contains 2. So comparatively, the intermolecular forces are weaker on this one, which means more molecules can escape, and increasing the vapor pressure, which means this one is going to have the lower vapor pressure. So that's my best advice on how to approach this type of problem. So go ahead and do daily work 12.3. So for each pair of compounds, once more, pick the one with the lower vapor pressure. Review what vapor pressure is. Visualize that the stronger the intermolecular forces are, the harder for the molecules to become gas. Therefore, less molecules to put pressure on the surface. So the stronger the forces, the lower the vapor pressure. And I would say this will be close to 30 minutes, so I will say let's stop here, and we will continue on part C with the part C, D, and E, and F with the remainder of the chapter. So until the next one, see you later. Take care.